So why do we describe soil profiles? You see here that we're going to do describe, classify, and interpret. First, we describe the soil to determine its properties. Once we've determined the properties, we use those to classify the soil. And once we've classified the soil properties, we use those to determine the uses and the limitations of that soil. So we're interpreting the properties. There are no reliable interpretations without proper classification, and there are no proper classifications and reliable classifications without a good description of the soil properties. We use dichotomous keys in soil taxonomy, which is a key that uses a series of yes-no questions. So our steps in classifying a soil profile involve, after we've dug the hole and we're looking at it, we identify the horizons and we describe the physical, chemical, and biological properties of each horizon. Then we assign the appropriate horizon designations. That's the master horizon, the A, B, C, O, R, whatever is appropriate. The sub-horizon that gives more information about it, such as T for clay accumulation, or G for glade, or P for plow layer. And then the number if both the master and the sub-horizon designations are the same. And then we use those characteristics to determine the diagnostic horizon classification using a dichotomous key, and then we'll use that in soil taxonomy once we know the diagnostic and horizons and moisture regimes to determine the soil order. And then using the diagnostic horizons, the moisture and temperature regimes, and other soil characteristics, we classify the soil to each of those lower levels of classification in taxonomy: suborder, great group, subgroup, and family. However, taxonomy is not used to identify the correct soil series. Soil series are regionally based concepts, soil profiles that have similar horizonation, depths, and characteristics, but they're geographically anchored, and taxonomy groups a lot of those soil profiles and soil series into larger categories of the families. So how would one of these work? If we have a surface epipedon, so the surface means epipedon, or epipedon means the surface soil, and we have a simplified diagnostic key here that uses that dichotomous pathway. So we ask the question, is the soil organic, the surface soil organic? And there are characteristics on that, is the thickness and the amount of organic carbon that it has to have. But essentially the question is this: is the surface soil organic? If the answer is yes, then we're looking at a histic horizon. If the answer is no, we have to ask another question. We are dealing with a mineral soil. So we look and see, does that surface mineral soil have soil structure? If the answer is no, we have an ochric A horizon, or an ochric epipedon. If the answer is yes, we go to our next diagnostic question that asks, what's the color of the soil? And those colors, if they are both value and chroma are 3 or less, we're going to go one way, but if they're not, we go back and we have an ochric horizon. If they are both 3 or less, we have a dark colored soil. We ask the next question, which is it more than 25 centimeters deep? If the answer is no, it's an ochric horizon. Now you notice the footnote associated with both of those. There are exceptions for the color and depth requirements under certain conditions, as noted below. But if the depth is greater than 25 centimeters, then we go to the next question, and we say, is the organic carbon content more than 0.6%, which is more than about 1% organic matter? If the answer is no, we have an ochric horizon. If the answer is yes, we go to our next question. Is the basic cation saturation percentage greater than 50%? If the answer is no, we have an umbric horizon, and if the answer is yes, we have a molic horizon. Again, this is a simplified key because there are several other surface horizons that are possible, but these are the most common. And even among these, the ones that are the most common here in central Illinois are ochric and molic. The epipedon key does not work as a dichotomous key, and it is much more complex than that one for epipedons. And so in working with students in soil judging contests and things like that, we look at the area we're in and we develop a key associated with that area. So for instance, in much of the Corn Belt, there's only 4 endopedons or subsurface diagnostic horizons to address: albic, argillic, spodic, and cambic. And then in order to determine the taxonomic classification, we go back and we use that dichotomous key. And although there are 12 orders in soil taxonomy, only 4 of those are common in the Corn Belt. And if you go further north, you can find some spodosols and maybe some histosols. And if you go further south, you have to go further south to find ultisols and vertisols. So if we look at endopedon characteristics, so these subsurface horizons, again, this is not a dichotomous key like the previous one. We look at the characteristics. An albic horizon is an eluvial horizon, and this is classified primarily based on color. So we're looking now at soils that are low in chroma and high value. So these are going to be think of them as grayish colored soils, especially when they're dry. So light color and not much intensity to that color. So low chromas, high values. And then spodic soils are illuvial horizons. They're low pH and they still have a great amount of organic carbon, even though they're a subsurface horizon, but that's because the organic carbon has been moving in. It's an illuvial accumulation of carbon and aluminum, and it may or may not have iron that's moved with it. And these typically appear redder or blacker or both than overlying horizons. An argillic horizon is an illuvial accumulation of clay. Now that actual amount of clay increases depends on the soil texture. At a minimum, it has to be at least 3% absolute, or 1.2 times the clay content of the overlying layer, until you get to soils with 40% clay and above. Then it's just an 8% increase absolute. Cambic horizons, again, are illuvial horizons, and these are horizons that have some evidence of soil development. Maybe they've got a weak structure forming, or colors are changing, so they don't look like the parent material anymore. But the primary way that we identify these, after we've decided, yes, there is some soil formation that's occurred, is they don't fit into the category of any of those other endopedons. So in this case, if we were going to ask the questions about the order, first question we start with, and this is the order that the key does them in, does the soil have a histic horizon? If it does, then it's a histosol. If it's not, we ask the next question. Does it have a spodic horizon? If it does, it's a spodosol. Now, these are the soils that are most common further north in the northern Great Lakes region. You find them in Michigan and Minnesota and Wisconsin. If it doesn't have a spodic horizon, we go to the next question. We ask, does it have a molic horizon? If the answer is yes, it's a mollisol. If the answer is no, we ask the next question. Does it have an ochric horizon? Well, if it's not a molic horizon, generally, most of the reasons, it's going to be an ochric horizon. Could be an umbric, but again, generally, and since we're talking generally about the Corn Belt, you won't run into the umbrics. So does it have an ochric horizon with an argillic horizon under that, and it has a base cation saturation percentage greater than 35%? Again, this is going to account for essentially all the argillic horizons you would find in the Corn Belt. Once you get into the southeast, those conditions change. If it meets these characteristics, then it's an alpha sol. And when we look at these two, then, the mollisols and the alpha sols are the dominant soils that occur in the Corn Belt. The mollisols in the grasslands and the alpha sols in the forested areas. If it doesn't have that, we go on to the next question, ask, does it have a cambic horizon? The answer is yes, it's an inceptisol. And if the answer is no, then we have one of our baby soils, an entisol, something that is just beginning to form. The inceptisols may be moving in a direction so that if the soil formation continues for another 100, 200 years, it will look like a different soil. And then the inceptisols and entisols are found in small isolated areas, and these are often associated with river systems.